Welcome back everyone. In this lecture we will actually complete the proof of Schroder-Bernstein theorem. So, first we need a lemma. So, let me start with that. So, let us say actually we have a set, let us call it x, and then what we are going to do, we are going to look at a function which is increasing function from the power set of x to x. So, let us say f is a function from power set of x to power set of x such that it is increasing. So, increasing with respect to inclusion. So, that means whenever A is subset of B subset of x, then that should imply that f of A is subset of f of B. Okay. So, this is what we call it as increasing function. F is a increasing function, and if you want to be very strict, then you have to call it as a non-decreasing function, but anyway it is clear that what we mean by this. So, now given this function which is actually satisfies this property. So, what we can do, we can actually guarantee that there is a fixed point for this function. That means there exists an element s inside the power set of x such that this f of s is exactly equal to s. Okay. So, that means s is a fixed point of this f. S is a fixed point element of this f. Okay. So, this is what we want to prove. Of course, we are in very special setup and proving that there exists a fixed point is not very difficult here. So, the most important thing is that we have to actually abstractly understand what is happening here. So, what one can do, we can actually collect the following collection of subsets, let us call it cal C. So, this is you collect all possible C inside the power set of x such that this C is indeed subset of f of C. So, let us take this weaker collection. Okay. So, we want f of s to be equal to s, but then that would imply that s is subset of f of s. Okay. So, that is already there. So, we are in some sense looking for all possible elements that satisfy this property. So, now whenever we actually define such a collection, we need to actually verify why it is non-empty. It is easy to see that the empty set is in this collection, because empty set is going to be contained in f of empty. F of empty, whatever it is, it could be empty set, but definitely empty set will be contained in f of empty. So, that tells you that empty set is in this collection. So, this collection is indeed non-empty collection. So, now what we are going to do, we are going to take all possible union of elements from this cal C. So, take S to be the union of C, where C comes from this cal C, and we are going to claim that this f of C is the fixed point that we are looking for. So, f of s should be equal to s, this is the claim. Okay. So, let us actually verify this. So, now if I start with C in C, then that would imply that C is subset of f of C. So, that is by definition. So, that means if I take the union of C in C, so that is our S. So, that is going to be contained in the union of f of C in C. Okay. So, this containment is already there. So, but what is f of s? So, f of s is going to be f of union of C in C. So, that tells you that this is exactly equal to union of f of C in C. So, that means this is exactly f of s. So, that proves that s is contained in f of s. So, this proves that f is contained, sorry, s is contained in f of s. So, now what is about the other way? So, now if you are taking for example element C in C, so then it is clear that C must be contained in f of C by definition. But now what we can do using f is increasing, we can see that f of c should be contained in f of c. So, that is already there. So, that implies that f of c is indeed element of this collection again. Okay. So, because it is an element again in the collection, that says that c is in c implies f of c is in c, and this is true for all c in c. Okay. So, this implies that whenever I am taking f of s, which is union of f of c, c in c. So, this is going to be subset of union of c, c in c, because all f of c lies inside the collection. So, that would lie in this the union, okay, which is exactly our S. So, this proves that the other way f of s is contained in S. So, here we had that S is contained in f of s, and then here we have that f of s is contained in S. So, that implies that S is equal to f of s, and S must be a fixed point. So, this completes that under our hypothesis that f is increasing, we can actually have a fixed point. So, now use this lemma and then prove this Schroder-Bernstein theorem. So, let us recall the statement. So, here is the theorem. So, what it says, whenever you have a injective maps from one set to another set, let us call them A and B, and then let us say I is, maybe we will call it F, no sure. F is from A to B, injective map, and then G is B to A, again it is an injective map. So, then this would implies that there exists a bijective map from A to B, and in particular that we have cardinality of A is same as cardinality of B. Okay. So, this is the statement. So, let us actually try to prove this statement using this previous lemma. So, for that what we are going to do, we are going to define this function capital F from this power set of A to power set of A. So, if you think about it, yeah, this function is motivated from looking for the fixed point that actually does the job. So, so it will be clear like once we define the function like why it is defined like that. So, define this capital F, which is a function from the power set of A to the power set of A, and which is defined to be, let us call it f of c, which is A difference g of B difference f of c. Okay. For all c comes from P of A. So, this is the function that we have defined. So, now the claim is that f is indeed increasing function. So, let us verify it is an increasing function. So, we start with let us say C1 and C2 coming from this P of A such that C1 is contained in C2. Okay. Now, using this we need to actually verify. So, now C1 is contained in C2, that would imply that that f of C1 is indeed contained in f of C2. Okay. So, now we are going to take the complement of this f of C1 inside B. So, that then we will get that B difference f of C1 or C2 will be contained in B difference f of C1. So, when you take the complement of something, then the inclusion reverses, and you see that we have twice the complement. So, once we are taking it here and once we are taking it here. So, that will actually negate with each other, then we will get the correct inclusion. So, when you start with C 1 subset of C 2, then f of C 1 must be subset of f of C 2, and B difference f of C 2 must be subset of B difference f of C 1. So, now what we can do? We can apply G again. So, from here we can apply G, that G of B difference f of C 2 will be subset of G of B difference f of C 1. So, now if we take the complement of this inside A, so then what do you get? You get A difference G of B difference f of C 1, which will be contained in A difference G of B difference f of C 2. So, that is because taking complement will reverse this inclusion. Okay. Then it becomes A difference of this included in A difference of this. Okay. So, that means you can see that f of C 1 is contained in f of C 2, because f of C by definition A difference G of B difference f of C. Okay. So, this proves that C 1 is contained in C 2 implies f of C 1 is contained in f of C 2. So, that means f is increasing. Now, using our earlier lemma, we can get that there exists a fixed point S, which is subset of A, such that f of S is exactly equal to S. So, now look at this S carefully using the pictorial way. So, you have this A and then you have this B. So, you can see that so some part of S is what there in this A, and then you have this A difference S. So, now you can see that S is mapping, okay, under F you get what is this f of S. Okay. So, now f of S is nothing but A difference, this capital F of S is nothing but A difference G of B difference f of S. In other words, so this is you are saying equal to S, this means A difference S should be equal to G of B difference f of S. Okay, this is what we have. That means that when we take this A difference S, then this is indeed mapped under G inverse, that it goes exactly to B difference of f of S. Okay. So, because G inverse of A difference S is exactly G of B difference f of S. So, this is what we are getting from here. Okay. So, this actually suggests what should be the bijective correspondence. So, if we focus on this S part, then S part should be mapped to f of S part using f, and then the complement of that, which is A difference S. So, that should be mapped to B difference f of S using G inverse. So, then it is clear that what should be the function that we are interested in defining. So, you define this h, which is a function from A to B, where h restricted to S is exactly f restricted to S. So, that is the f that we are getting here, and then you take h restricted to A difference S as G inverse restricted to G of B difference f of S, because the G inverse of A difference S is exactly equal to B difference of f of s. So, that means if you are interested in a map from A difference S to B difference f of s, you take the G inverse map. So, that is what we are taking. So, which is a map from A difference to B difference f of s. So, the way we constructed, you can see that it is a well defined map and it is injective at each part. So, that gives you H is injective function. So, now it is also surjective because the image of H of A, you can write it as H of S union H of A difference S, which is exactly H of S is f of s union H of A difference S is exactly B difference f of s. So, that gives us exactly B. So, this implies that this is indeed bijective function from A to B. So, that proves that the cardinality of A equal to cardinality of B. So, this implies that cardinality of A is same as cardinality of B for any two sets A B that satisfies the property that we stated in the theorem. So, whenever you have injective function, so then modulo this theorem, it is okay to write the cardinality of A is less than or equal to cardinality of B. So, whenever you have an injective function from A to B, injective map, so then you can always denote this by the cardinality of A less than or equal to cardinal of B. So, this actually gives you a comparison between cardinality of any two sets. Even for infinite sets, one will be able to actually compare their cardinality using this notation now. So, now what is the meaning of cardinality of A being less than cardinality of B? That means there exists an injective function from A to B, there is an injective function, but there is no equality happening. So, that means there is no surjective function, there is no surjective map J from B to A, because the both cardinality cannot be same. Okay, if there is a surjective map, it is not difficult to see, like if the cardinalities are same, then you can see that there is a bijective map from A to B that will give you surjective map from B to A, and so this implies that cardinality of A should be less than cardinality of B and the cardinality of A should be different from cardinality of B. Okay, but that is what we wanted. Okay. Now, using Cantor's theorem, one can actually see that the cardinality of n and the cardinality of power set of n, they never actually matches. So, recall the Cantor's theorem. So, the Cantor's theorem compares the cardinality of x and the power set of x. So, basically it says that there is no onto map or surjective map from x onto power set of x. Okay. So, that means the cardinality of x always should be less than the cardinality of power set of x. So, what we conclude from this, there is an inclusion from x to power set of x. So, you can take some small x in x and then send it to this singleton x. So, that is giving you injective map from x to power set of x. So, now using Cantor's theorem, you can see that there is no onto map from x onto power set of x. So, that says that the cardinality of x should be less than the cardinality of power set of x, and this is true in general, not only for finite set, it is even true for infinite sets. So, that would say immediately that the cardinality of n is strictly less than the cardinality of power set of n, and which is strictly less than the cardinality of power set of n, and so on. So, this actually kind of gives various different infinities For example, the cardinality of n, which is the first infinity that we see, we call it as aleph naught, and the cardinality of power set of n, which is same as the cardinality of the real numbers. So, this is aleph 1, this is aleph 2 and so on. Okay. So, this actually kind of gives comparison between infinite sets. For example, we can ask like the complex numbers, whether it is like have same cardinality as power set of n, or the same cardinality as power set of n and so on. Okay. So, different clearly using Cantor's theorem that all these infinities, they are all different, and one should be able to actually compare given set to this set. But unfortunately, in practice it is not that difficult to compare given set to like the cardinalities of the power set of n and so on. So, that becomes actually very difficult. For example, there is something called continuum hypothesis, and which asks that question that is there any set having a cardinality in between the natural numbers and its power set. Okay, let me just state this continuum hypothesis. So, usually the continuum hypothesis stated between natural numbers and real, because real and power set of n, they have same cardinality. So, one can actually state it between n and power set of n as well. Okay. So, what continuum hypothesis asks, is there any set A that having cardinality between natural numbers and the power set of natural numbers. That means, we want the cardinality of A should be greater than the cardinality of n and the cardinality of power set of n, okay, which is same as cardinality of R. So, one can replace this as follows. So, one can actually say that is there any subset of real numbers, let us call it A, such that the cardinality of A lies between the cardinality of n and the cardinality of R. Okay. So, basically we want an infinite set A such that whose cardinality is different from the cardinality of n and the cardinality of R. And this is what called continuum hypothesis. Actually, Paul Cohen, he won a Fields medal for proving that this question can neither be proven or disproven using ZFC axioms. So, indeed Paul Cohen, so he proved that. So, this continuum hypothesis can neither be proven or disproven using only ZFC axioms. Okay. So, that means like if we are going to assume only ZFC axioms, so then we do not know whether such set exists or not, and it is commonly believed that such a set does not exist. So, I will leave it to you to think about it. Okay. So, now like you can go back to this Schroder-Bernstein's theorem, which actually kind of tells that if you have a map injective map from A to B and injective map from B to A, then we will be able to say that the cardinality of A is same as the cardinality of B. So, now as an immediate corollary, what one can actually get if we have an injective map from A to A. So, let us say I have an injective map from A to A and A is a set. Okay. So, then we can actually take a subset of A, for example, like which lies between the f of A and A. So, let any C which is there in between these two. So, it is clear that A and f of A, they have same cardinality because f is bijective function from A to f of A. So, now if I start with any set which is actually between f of A and A, then that would imply that the cardinality of A is same as the cardinality of f of A. So, this you can get it as a immediate corollary because we already have this inclusion from C to A. So, this is just given by what is called inclusion, x goes to x. So, this implies the cardinality of C is less than or equal to cardinality of A. So, now that we have this function f which is a function from A to A, but technically speaking I can actually restrict the Go domain. So, I can think this is a function from A to C. So, since it is injective map, then we get that the cardinality of A must be less than or equal to cardinality of C. So, now given these two, using Schroder-Bernstein theorem, we get that the cardinality of A should be equal to cardinality of C. So, this way we can see that we will be able to get plenty of sets between A and f of A whose cardinality will be same as this C. So, for example, if we are actually able to get a injective function like I said from R to close comma 0 comma 1. So, then if I take any set between 0 comma 1 and C, so then let us say this is injective. So, I will leave it, I have left it as exercise to construct this injective function. So, now using our corollary we can see that for any set C we will have that cardinality of C same as the cardinality of R, which is same as the cardinality of 0 comma 1. Okay. Sorry, I wanted to do the other way. So, let us say we take any set between as a corollary you take any set between 0 comma 1 and then R, then that would imply that the cardinality of 0 comma 1 is same as the cardinality of C, which is same as the cardinality of. Okay. And this is something like easy to prove, but it comes for free from Schroder-Bernstein theorem. Okay. So, there is an alternative way actually one can actually iteratively construct this fixed point thing. So, maybe I will leave it that not a problem. Okay. So, so this actually completes the discussion on the counting cardinality of sets. So, now what we are going to do, like after this actually we will construct the set of integers and the set of rationals using equivalence relations. Then that will actually kind of complete the section on set theory. Then after that we will move on to actually more practical problems on counting. So, we will actually establish some basic counting techniques that actually help us to do counting of some natural sets that actually arises in combinatorics and graph theory and so on. Okay, I will stop here and we will continue with construction of integers and rational numbers in the next class. Thank you. I will stop here.